Hello everyone, this is David Cuttress here from the KE Hub at Aberystwyth University. We're working in conjunction with Farming Connect to provide current and applicable scientific knowledge to the agricultural industry. Today I'm going to read a technical article called Carbon and Climate Change, an Overview. You can find a copy of this technical article as well as a library of other articles for free on the Farming Connect website. What is climate change? Climate change refers to a meaningful statistical change in the state or variability of the climate, which can loosely be defined as the average weather over a period of time. The main climatic pattern change associated with the term climate change is the increase of global average temperatures. Whilst many view climate change as an inherently human-associated process due to its consistent representation in the media, climate change does also inherently occur naturally over time. However, research has noted an acceleration in climate change towards increased temperatures, which correlates exactly with human activity, particularly following historical industrialization. As such, climate change is often specified to be related to direct and indirect human activity, as noted by the United Nations Framework Convention on Climate Change. And the term climate variability is used to discuss natural causes of change. Climate variability has demonstrated natural cycling of cold, glacial, and warmer interglacial periods, which occur over thousands or tens of thousands of years. This normally gradual changing of temperature, which can fluctuate in range of over 11 degrees C, can be linked to shifts in the Earth's orbit along with volcanic eruptions and changes in the Sun's solar activity. One of the key ways science allows us to ascertain climate change is through monitoring of the polar ice sheets. Ice sheets have developed over hundreds of thousands of years and within them contain trapped air bubbles which act as a snapshot of the period's atmospheric gas levels. The trend observed over the last 1,000 years demonstrates a significant increase in gases associated with climate change, becoming present in higher concentrations as human industrial activity becomes more common, from the 1760s onwards. Another term which has direct links to climate change and tends to focus on the effects of human activity is global warming. As it implies, this focuses on the noted trend of the surface warming effects via climate change. What are greenhouse gases? The process which causes the increase of temperatures related to current climate change patterns is referred to as the greenhouse effect. This process involves the observation that certain atmospheric gases act similarly to glass in a greenhouse, in that they allow shorter wavelength radiation from the sun through, but absorb and radiate in all directions the longer infrared radiation reflected back from the Earth's surface. The gases in the atmosphere which act to absorb and re-radiate heat have commonly become referred to as greenhouse gases, and it is high quantities of these which can cause global temperatures to increase. Greenhouse gases include water vapour, H2O, carbon dioxide, CO2, methane, CH4, nitrous oxide, N2O, sulfur hexafluoride, SF6, hydrofluorocarbons, HFCs, and perfluorocarbons, PFCs. 4 of these greenhouse gas groups contain carbon molecules, and within these, CO2 makes up the largest proportion. The most recent figures suggest that CO2 is present in 407.8 parts per million in the atmosphere. This further demonstrates a continuing annual trend of increases. As such, carbon often becomes a proxy term for discussing greenhouse gases or climate change in general. Current concentrations of CO2 are more than 200 times higher than all other human activity-related greenhouse gases combined. As such, CO2 is considered the single biggest contributor to climate change. Changes to the net amount of energy which reaches the Earth's surface are discussed in regards to radiative forcing, with positive radiative forcing increasing the Earth's surface temperatures and negative radiative forcing having the opposite effect. Both are measured in watts per square metre. A common measurement which is based on radiative forcing is global warming potential. This looks at the total radiative forcing effect over time per unit of gas in relation to CO2 as a set standard, where CO2's global warming potential is considered 1. One of the most significant impacts which leads to the increased presence of greenhouse gases in the atmosphere was the initial discovery that burning fossil fuels produces energy. Fossil fuels had previously acted as long-term storage of carbon. Between 1750 and 2011, fossil fuels combustion has accounted for over 70% of all human-related CO2 present in the atmosphere, demonstrating its significant impact. Methane and nitrous oxide emissions are the second and third highest emissions respectively, with 16% and 6% of all greenhouse gases. More than half of all methane produced originates from microbial sources, whether these are within the ruminant stomachs, rice paddies, or the soil itself. Recent research suggests a compounding effect of rising temperatures as climate change effects cause increasingly ideal environments in which these microbes might thrive. Increased microbial activity and stability will therefore lead to increased methane and nitrous oxide production. The largest contributor of nitrous oxide is suggested to be fertilizers used in agricultural practices, as these are cycled through nitrification and denitrification via microbes in the soil. Carbon and carbon equivalents. Carbon is a crucial element for all life on Earth. It is present in animals, plants, rocks, oceans, the soils, and it cycles between these, allowing its continued redistribution into various sources or carbon sinks. Whilst there are complex considerations involved in carbon cycling concerning naturally produced organic carbon sources, as well as artificial inorganic sources, the key consideration for climate change involves the balance of emissions of inorganic carbon dioxide and its storage or sequestration into the land and the oceans. Land sequestration. Sequestration of CO2 in land systems occurs almost entirely through photosynthesis, where CO2 is converted to sugars within plants and released back as oxygen. Therefore, vegetation, particularly forestry, acts as a vital carbon sink. However, increasing temperatures associated with climate change patterns may limit photosynthesis through various mechanisms, leading to saturation points eventually being reached. Sequestration, essentially storage, of carbon into vegetation leads to its conversion to soil organic carbon, SOC. This cycling is linked both directly to plant growth, plant-soil microbiome interactions, and plant deaths through decomposition. There are direct routes for sequestration of carbon, independent of plants into soils. However, the sequestration values are comparatively low and carbon is far less effectively sequestered long term. Ocean sequestration. Our oceans are said to have absorbed 41% of the human activity-related CO2 being emitted into the atmosphere to date, and as such are considered significantly beneficial as a carbon sink. One main route of sequestration within the ocean involves the biological incorporation of carbon through marine photosynthesis via phytoplankton and others into marine organisms through consumption. Following consumption, there is vertical cycling of carbon as dead organisms sinks to the ocean depths. This vertical gradient of carbon is often referred to as carbon biological pumping. Equally, a physical pump system exists, whereby atmospheric CO2 dissolves at the surface of the ocean and is circulated into deep oceans through convection currents. Whilst oceans act as a carbon sink, many other aquatic systems, lakes and rivers for example, are considered to be opposingly involved in the net emission of carbon dioxide. However, one other set of aquatic systems which is demonstrated to act as a sink of carbon are glacier-fed rivers and lakes. These contain high levels of minerals, particularly carbonate and silicate, which can actively remove CO2 via weathering processes. An important concept when considering the impact of CO2 on climate change is that its presence in the atmosphere is cumulative. Therefore, any emissions which are not sequestered long-term by the land or our oceans remain in the atmosphere and are additive on top of all future emissions. This principle influenced the formation of the social cost of carbon, a concept which influences the implementation of climate change policies, climate change caps, and costing of carbon outputs. Global climate change. Globally, the trends of climate change over the last several hundred years have led to a 1 to 1.2 degrees C increase in average land temperatures. Alongside this, a significant proportion of work suggests increases in climate extremes globally. The extremes include higher levels of rainfall leading to more intensive flooding, whilst other regions are experiencing more intense and longer droughts. A high level of agreement has been reached on models of climate patterns which predict substantive warming by the end of the 21st century at our current rate of emissions, with extreme maximum temperatures set to rise by up to 5 degrees C and become more frequent. Increasing temperatures appear linked to increasing sea ice presence and glacial melting, which are thought to be the main drivers for increasing sea levels. Globally, emissions per sector suggest that electricity and heat production, along with agriculture and land use-based sectors, are the biggest contributors of greenhouse gases. UK climate change. In the UK, the most recent comprehensive report of our weather patterns from 2018 demonstrated increasing heating trends. On average, a 0.3 degrees C increase in land temperature has been documented since 2009, and an average increase of 0.9 degrees C compared to the period between 1961 and 1990 has been observed. This matches with the occurrence of our 7th warmest year in 2018 in the UK since 1884, with all of the top 10 warmest years since 1884 occurring between 2002 and 2018. Alongside these figures, the UK has also experienced some extreme weather patterns, including the highest UK December temperature on record of 18.7 degrees C in 2019, a new UK world record temperature of 38.7 degrees C in 2019, the warmest, driest summer in over 100 years in 2018, and most extreme rainfall in South Wales in 50 years in 2018. The UK is currently considered to be the country with the 8th highest emission of CO2 when scaled per head of population, and the 15th highest country when direct emissions are analysed. The UK has, however, seen a gradual decrease in the emission levels within the last 30 years, with 44% reductions in total greenhouse gas production and 39% reductions in CO2 specifically. This trend correlates significantly with our change in reliance on coal as a fuel source. Agriculture and climate change. Agriculture can be seen to be having significant effects on both regional and global greenhouse gas emissions. In the most recent figures from the Department of Environment, Food and Rural Affairs, the UK ranked the 12th highest country for CO2 emissions per dollar of agricultural production. Agriculture and land-based emissions which are contributing to this can come from many sources, including livestock through direct emissions, feed production and processing, manure and slurry through their storage and spreading procedures, management of grasslands and crops through fertilizers and other chemical applications which can influence greenhouse gas production directly or indirectly, soil management through processing of fertilizers, the drainage of peat and compaction and other physical factors, farm infrastructure and transport through fuel use, heating, electricity, machinery production and food processing. However, natural and agricultural land-based systems also offer opportunities for some of the most substantive approaches through which we can increase our sequestration and mitigation of global climate change. This is particularly possible through maintenance or creation of carbon sinks such as soils. Key carbon sinks to consider in agriculture include vegetation via inclusion of riparian strips, mixed species grasslands or protected scrublands, forestry through agroforestry practices and hedgerow plantations, soils through appropriate management of soil health, reduced or no-till farming and many other methods. Research suggests that warming environment related to climate change will have a mixture of beneficial and detrimental effects directly on farmers. Warmer temperatures and increased CO2 may well increase the life cycle speed of grain crop production, though other crops which are more temperately adapted or sensitive to change may suffer. Equally, the likelihood of more extreme flood and drought scenarios may significantly stress farmers and their crops and outdoor livestock productivity. Alongside this, longer summers and warmer winters will likely increase disease pressures on crops and animals, as cold winter periods often act to halt or kill disease vectors. In summary, over the last several hundred years following industrialization, there has been increasing evidence of statistically meaningful increases in global temperatures. This suggests human activity is having an increased climate change effect. The main human factors affecting this global warming are the increased production of greenhouse gases produced through a variety of processes across multiple sectors. Whilst greenhouse gas figures globally are still increasing overall, the UK has seen some decline in its emissions. However, there are still further gains to be made in combating greenhouse gas production and accumulation in the Earth's atmosphere. Agricultural, forestry land is a substantial emitter of greenhouse gases, but conversely has a huge potential to be utilised as a mitigating sector through the role of trees, vegetation and soils to act as carbon sinks. Takeaway messages are: current trends show climate change due to human influences such as major industrialisation are having a significant effect on global climate patterns. The biggest single factor driving climate change is the emission of carbon compounds, particularly carbon dioxide, CO2. Agriculture and the land use sector is one of the biggest influences on climate change globally through greenhouse gas emissions and reductions via natural carbon sinks. However, this sector also offers significant potential for removing greenhouse gases.